Okay, so chapter 6. Chapter 6 is very short, but it is packed tight. There's lots of information in here. Specifically, you're going to talk about friction, you're going to talk about drag, and we're going to talk about rotational forces, centripetal force. Okay? We've talked about friction previously. Okay? We've talked about kinetic friction and static friction in the first year course. This is very similar to it, and it's going to have a lot of the same properties. We're just going to do a little bit more problem solving. So now, essentially what friction, first of all, what is friction? What causes friction? The usual way to describe it, and even kind of shows this a little bit in the book, is by talking about two rough surfaces sliding over top of each other. That's not exactly true. Okay? What happens, okay, if you get two very highly polished pieces of metal, they're what's called cold welded to each other. It's very hard to slide them past one another. In fact, it's very hard to pull them apart at that point. Essentially what happens is that they are stuck together by the forces of friction because of the electrostatic force between the atoms on one side and the atoms on the other side, on the other piece. Okay? So friction is actually an electrostatic force. So now, the two surfaces don't actually even touch each other. It's just the proximity to each other. The atoms are in proximity to one another, and they attract one another. So now, the basic idea of friction, so far as it's modeled, it's not an exact equation. This is an empirical formula, which means that we don't know, we don't have the equation that we're deriving from first principles. We're deriving it from data. And there's nothing wrong with that, especially when we're working on trying to make an equation work. What we have here is that the frictional force, okay, whether it's kinetic or static, when we're talking about mass. Okay. Well, I'll talk about static friction force. This is going to be less than or equal to US times the normal force. Okay? Again, it's how hard one surface is pressing against another surface. All right? It doesn't necessarily equal the weight. It doesn't necessarily equal the sine or cosine of the weight times the weight. Okay? Because there could be an applied force there too. Remember the problem that we did in chapter 5, where you had the force being applied into the ramp. Okay? That will significantly change the frictional force. Now, static friction. Static friction is the force that is required to get something to start moving. Okay. So this only matches the force that's trying to make it move. Right? It doesn't. So this actually is a variable. It doesn't necessarily equal US times Fm. Just erase that. Okay. It doesn't necessarily equal this coefficient of friction of static friction US times the normal force. Okay? It just matches whatever it is it's trying to get it to move until it can't match it anymore. So there is a max value of static friction, which we say is equal to US times Fm. And I should make a little max statement. Okay? So FRS max is equal to US times Fm. Now, when something's already moving, you have kinetic friction. Kinetic friction is the friction that opposes motion. Okay? There are some subtle things that we're going to have to do. It doesn't always oppose motion, it opposes sliding between two surfaces. We've come to find out that static friction can actually be involved with something that's moving. Not in this chapter, in later chapters. We're going to get to it. It seems kind of weird, but that's the way it works. Okay? And that's kinetic friction is going to be mu k times Fn. So now, This mu k, okay, that is the coefficient of friction. That is when you have two surfaces that are sliding over top of one another. It's not when one object is moving, it's when two surfaces are sliding past one another. That's a very key difference. We're going to get to it when we get into rolling in about chapter 8 or 9. Okay? Now, one thing that we have found almost always, mu k is less than us. Yeah, you might want to put an equal sign, less than or equal to us. There's somewhere it's just about equal, and for the purposes of our measurement here, it is pretty much, some of them will be pretty much equal. We're only talking about 2, maybe 3 sig figs in this. Beyond that, really, other factors can play a larger role beyond a third significant digit. Okay, so usually we get, almost always we get the kinetic friction being less than the static friction. Can't speak to it for every case. There might be some cases where it doesn't. But so far as I know, and might want to do some research, see if you can find one where, and I'll give you a little extra credit. I'll give you 1 point extra credit. If you can find one where mu k is greater than us. And we can confirm. All right. So now, how does that involve problems that we're going to do? Let's say we have this. Right, we're going to do a problem. This is very similar to the problem that we did in chapter 5. We have a mass here. And I'm just going to put an angle theta here. And I'm going to do an applied force here. We want to know what the acceleration is going to be. Well, in order to figure out the acceleration, we have to know the motion. We don't have to know which way it's accelerating. We just have to know the direction of the motion. So I'm going to tell you, initially, this will slide up the ramp. So at a v0 initial velocity, it's going to go up the ramp. We want to figure out, we want to come up with a literal expression for the acceleration of this box, either up or down the ramp. And it's initially moving up the ramp doesn't mean that the acceleration is up. So we draw a free body diagram. mg. Normal force is going up. Okay, I'm going to make this push here in the original picture. I'm going to make it a pull. It's a little bit easier to work with. Applied force goes this way. And friction, because it's sliding up the ramp, friction is going to go like this. I'm going to call it Fr. And I usually like to put mass. So now we want to figure out the accelerations. Okay, so now I've chosen my body. It's the mass, that's not very hard. Step 2, identify all forces acting on the body. Applied force, kinetic friction, mg, normal force. Draw a free body diagram, check. Step 4, choose appropriate reference system. Okay, I always like to make it so that my acceleration goes along an axis. It turns out that this angle is theta right here, and this angle is theta. Now, like I mentioned today, the x component here, okay, we're referencing from the y-axis. The x component here is going to be sine, because it's going opposite the angle theta. Fa down the bottom. If I draw a line here, and I get the x component of this, that's going along our reference axis. It's adjacent to angle theta. Use cosine. So let's figure out, let's do our sum of all forces equation. It's still the same idea. But now we have to use that normal force. So if I do sum of all forces in the x and sum of all forces in the y, what do I have? Sum of all forces in the x. This is, we always start with the direction it's going to accelerate. Okay, we're going to start with the direction it's going to accelerate because if you have, if you don't have to use the y direction, then don't do it. You're going to have to, but it's always good to start off, see if I can avoid using a second equation. Well, in the x direction here, I have FRK, and I'm going to assume the positive direction to be the direction that this is initially moving. E0 is going up the ramp, so I'm going to make up the ramp positive. Okay? I'm making y this way, x this way. If you really want to know, z is going to go into the board, but that's not important to make a right coordinate system. So negative FRK going down the ramp. I've got mg sine theta going down the ramp, so that's negative. And then I have this portion of Fa. Okay? As I mentioned before, that's going to be positive and cosine. This will equal mass times acceleration. Okay, so what unknowns do I have here? Okay, we're going to assume that I know what Fa is. We're going to assume that I know what the mass is and what theta is. I don't know what FRK is. Right? So I have to solve for FRK in order to get this in terms of acceleration. You can't just say, oh, well, I'll solve it in terms of acceleration. We're going to solve this in terms of m, g, theta, and Fa. Yeah, okay. Now, FRK is not one of these four. And the AP test loves putting these equations on. So now, I gotta say, all right, sum of all forces in the y direction. In the y direction, your acceleration equals 0. What it would mean if you're accelerating in the y direction is that you're going off the ramp. You're either jumping off the ramp or boring into the ramp. Right? We're not doing that. We're assuming that we have a rigid ramp and this applied force that's pushing into it isn't going to drive through the ramp. That's the only way that you have an acceleration in the y direction. That'd be an incredibly complicated problem to do. So that's not what we have here. Right? In the y direction, we just have a balance. We have a balance between the positive y direction, which would be the normal force, and the negative y direction, which includes the applied force and this portion of mg. In the y direction, I've got this for Fa. Fa references from the x-axis. So we have familiar sine theta when dealing with the y direction. Problem is mg. Again, mg is referencing from the y-axis. Okay, so Fa is referencing from the x. Mg is referencing from the y. So because it's referencing from the y-axis, mg has to flip it, sine and cosine. So cosine goes in the y direction. Now, I do all this because I have to get what FRK is. There's no FRK in this equation. However, I do know that FRK is equal to UK times Fa. So now I have to do a substitution. Yes, questions like this are on the AP exam. Yes, you have to do big, long substitutions like this. So now, I plug in for my normal force. FRK is equal to UK times this whole thing. UK Fa sine theta plus UK mg cos theta. Yes, I've got to substitute this whole thing in up here. So I substitute negative FRK, so I've got negative UK Fa sine theta minus UK mg cos theta minus mg sine theta plus Fa cos theta equals ma. So we've got this big long equation solving for the acceleration. You divide out by A, divide out an N, okay? So if I do that, my acceleration, it's not really helping me all that much. I usually like to make positive first, so I've got FA over the mass times cosine theta minus mu k FA over m sine theta minus mu k g cos theta minus g sine theta. Okay. Now, a couple things that we want to check on. We want to make sure that our units are still acceleration. G is an acceleration times a unitless sine theta. Mu k. What are the units of mu k? Remember, mu k is equal to the kinetic friction over the normal force. A force over a force. So the units of mu k are null. Okay, it's unitless. Excuse the expression. Okay. It was a funny joke in the 90s. Leave me alone. Okay, so this is our equation. Okay, let's just go through again. So this is unitless. Cosine theta is unitless. We're left with g. Check. Sine theta, unitless. UK, unitless. Force over a mass. Kilogram meter per second squared divided by kilogram meter per second squared, check. Force over a mass, that's acceleration. Cosine theta, check. Okay, so now, this all checks out. Remember, the only thing that's really pushing it up the ramp, okay? And now let's see if this makes sense conceptually. Okay, let's make sure, this is the math. Let's make sense of this big long equation. G sine theta. G sine theta is what's trying to pull this down the ramp. That's gravity that's trying to pull it down the ramp. Okay? If I didn't have any friction or applied force, and I let this go, it would accelerate down the ramp at G sine theta. Check. Okay. Mu k, G cosine theta. Let's come back to that. Let's come back to this one. The applied force over the mass times cosine theta. Okay, this is the force into the board that's trying to push it up the ramp. Okay, this should be positive. That makes sense. Okay, now these two terms are a little confusing. All right, essentially this has to do. These are our friction terms. All right, so now mu k g cosine theta and mu k fa over m sine theta. This specifically is what we're dealing with friction. Okay, this is just, and this is another friction term. All right, I'm going to leave it at that. All right, I'll talk about drag in class. So without further ado, let's shut that down.